I will try not to make the same mistake.
This meeting is being recorded.
All right. So everybody go ahead and acknowledge that. And I will, let's see here. Okay. Got it. All right. So everybody is seeing the meeting slides there. And please do mute yourself. Our presenter, Mr. Green, is online there. I see him in the among the little windows. So we will. I'll mention you a little bit later here, but thank you for coming. Let me see. Okay. Come on. Okay, here we go. All right, well, welcome everybody to the May meeting of the Seattle Robotics Society. Glad you guys could come. And we will kind of follow our typical agenda here, so I won't go into a lot of detail with that. Let's see. Actually, that's not, no, sorry. Let me get back to the right one here. There we go. That's better. Okay. I was like, I knew that didn't look right for some reason, so now it does. So I will go ahead and just kind of roll quickly through these things. Please mute your microphones if you are not actively sharing, so we try to avoid background noise and things of that sort. And have a chat window open on your computer there, and that's a great place to put in questions. And also, if you want to share links or information on the web with everybody else, please put them in there. That goes into the post meeting information post that I put out, where I share this video, and then also all of the stuff from the chat. So anything you want captured and shared for everybody to see, please put it in there. And I did get a chance to send a message off to Kevin Ross to ask him whether they're getting close to being able to let us use their new facility. I'm hopeful that will be happening soon, but do not know anything new yet. I don't know if anybody else has got any information on that, but so anyway, if you're you can Google this address you see on the slide there if you're interested in seeing what the area looks like. This won't actually show you the specific building because this is all part of a big warehouse complex, and so this the actual address is kind of like way in off the road. And Google will get you to the road where you turn in, and then it's about 2 blocks back to where the facility is actually located. Got the new website is up and running. Hopefully you've all had a chance to take a look at that. And so far so good. Occasionally it took me, well, I didn't realize that there was an issue with uploading last month's video to YouTube, because it takes a while for it to process and post, and it got stuck for some reason. So it should have finished. I had everything kind of set up, a link and all of that in the website post, but since the video never actually finished processing, it never posted to our website. So thank you, Robert Kellogg, for pointing that out. I went back in, re-uploaded it, reprocessed it, and then it worked the second time. So go figure, We're planning to do hybrid meetings, online plus in person, once we resume in-person gatherings. So those of you who are not locals to Seattle, or for whatever reason you can't make it to the physical meeting place, we will have online access available for you. So we'll probably just need some people that come to kind of help me run equipment. So I'm still doing robotic classes with some junior high kids in Burien, and that'll continue at least for this year. So having some fun using the particular ones that we're using right now are the blue ones that you see in the slide there. They're pretty cool. Events that are coming this last week. There was actually over the last couple of weeks has been several. Let's see, what do they call it? DEED, Drive Electric something day. Anyway, there's events going on all over the country, and there was a number of them going on here locally. There's also some more coming up in the fall. Last week of September, I believe, is kind of the official National Drive Electric Week. So there'll be some more stuff then. And there may also be some First Washington robotics events if you're interested in those. Online presenters, I'm actually doing pretty good. I've got sent out a whole boatload of invites last night, and got through about half of my list, and so I'm going to do some more of those. So we're starting to fill out the rest of this year, and then hopefully into next year. This is what's coming up this year, and so I'm the August meeting may be a facilitated discussion, or if a presenter actually wants that slot, I will relinquish that. But I'm kind of planning on having a presentation of some sort then. And then October on is open, and so we're planning on filling up as many of those as possible into next year. Open discussions, if we have them, can be on a variety of topics. The next one that I'm kind of leaning towards is possibly something related to medical telemedicine and medical technologies that you can actually buy online. So there's a great deal of stuff that you can get on your own, and you can have in your home to measure, physiological things, and then connect with a doctor using the data that those things collect. So a little bit later, we will have
Robotics Society meeting.
Oh, okay.
Who's I hear somebody talking there.
That's me. Sorry.
Oh, please mute your mic. Thank you. Welcome, by the way. Kevin Green is going to be sharing with us his about stuff he's been doing with walk-in robots, and this particular picture here, I believe, is Cassie. And there's some pretty cool stuff down there at Oregon State University. Is that right? Give me a thumbs up there, Kevin. I think so. And so we will get to those a little bit later. Let's see. Am I seeing? Kind of curious. It's like I'm looking for update. I'm looking for the screens to update here, and I'm not actually seeing a whole lot of activity. So I'm hoping you guys are all getting that. Can
Yes, Steve, we're seeing the Robothon committee page.
Okay, and you're hearing me okay, right?
Yep.
Okay. Yeah, it's just the well, yeah. Actually, you know what I know it probably is. My wife is she's actually on a Zoom conference. It's just a one-way thing with a ton of people downstairs at the same time. So I have a feeling that she's probably limiting my bandwidth here. So it's like, anyway, okay. Well, I will continue. Thank you so much for the feedback there. Lloyd, would you like to share a little bit about Robothon stuff coming this year?
Yep. So basically, I think we've already announced this. We will not be having an in-person event this year. We're still looking at next year. We'll see how that goes. It's kind of just, play it by ear with COVID. We do have another virtual Robothon exhibition coming up, and we're shooting for August 27th from 12 p.m. to 3 p.m. This will basically be like we did before. We're going to have a collection of people presenting, short presentations of whatever they would like. So if you've got something that you're thinking about presenting, get in touch with Donna, I think Donna's already sent out a few queries. I think we have slot for one more person. I'm not sure. I know we have a couple people lined up, and I think we had a slot for one or two more. But yeah, pretty much we're continuing to do stuff, but keep it all virtual.
Yeah. So do you know if is it 5 or 6, or not sure how many people she's trying to line up?
I think, actually looking at, yeah, she's got about, from your slide, she's got about 4 presenters, and I think we cap it at 6.
Okay.
I forgot to look at my last notes right before the meeting.
Yeah,
so I know we've got spots for about another 2. And I know we've got some presenters. So
and we're always happy to, if we go over that number, we're always happy to take your name down, and if we get enough additional people, we can just schedule another event. So
well, and to that point, that's what happened, I think, with the first 2 presenters in this one. They're overflow from the last event. So these are actually working out pretty well. I mean, I'm pleased. We've had good attendance, we've had good presenters, and people seem to enjoy it. So we actually will continue doing some form of this even when we go back to live events, in-person events. This is, if you can't, if you want to do something and you don't think you're going to be able to make the August date, keep it in mind, because we're going to probably do at least one of these every year, even when we go back to in person. So maybe we'll do this in the winter or something when everybody's hunkered down inside. I don't know, but this, just like the hybrid meetings, this is something that kind of came out of COVID that's worth keeping. So we'll keep it.
Yeah, and having, I mean, the Robothon events are cool, but they only happen once a year, and it'd be nice to have something else to.
And frankly, the Robothon events are a lot of work to put together. And thank you to everybody who volunteers to help with that. These virtual exhibitions, by comparison, are pretty lightweight, so we can do these as frequently as we have presenters. And I guess the difference there is too, if it's a short topic, like 20 minutes or so, it goes in the virtual exhibition stuff. If it's like an hour-long presentation, check with Steve and do a full event or do a full meeting.
A meeting presentation. Yeah. Yep. Okay. All right. Anything else?
That's all I got.
All right.
Thanks, Steve.
Okay. Let's see, was it last Saturday, or maybe it was 2 weeks ago? I think it was last Saturday. They had the SRS PopCan Challenge test run up at the Snowco Makerspace in Snohomish, and so I was not able to attend that. I don't know if anybody here who's online was there, can share anything at all about that event. Does anybody?
Yeah, I can share about that.
Okay.
Yeah, it was 2 weeks ago. Our meetings are offset by 2 weeks from the SRS meetings, so we just did it over our meeting up there. We had 3 robots that came and attended. I think we successfully got 2 people interested in building some robots before the October 1st actual challenge that we're going to run at the Makerspace. We found that we can actually just barely fit the arena in the Makerspace shop, which is handy. To be honest with you, we ended up talking more about robots and practicing. We got a little bit of practice in, but there were so many people that showed up and had so many questions about things that I think I spent 90% of my time talking about my robot versus actually getting to run in. I'm sure Craig's on, right? Was that the same for you, Greg?
Yes, very much so.
Yeah, but it was great. It was really fun to talk about them too.
Yeah.
And we scored some really cool lithium-ion batteries from a guy that shows up like once a year, and he gave us these pretty snazzy batteries that have this battery management system you can communicate through over I2C, and that was kind of cool too. So free stuff.
Nice.
Yeah.
Nice. Cool. Well, it sounds like it was a successful event.
Oh, yeah.
Maybe didn't accomplish everything that you had hoped for, but it sounds like you did get some good stuff done, though, and it's always good to kind of get the word out there and be able to share with people about robotics. So
yeah, it was a blast. It was a good one.
All right. Okay. Yeah. Okay. So Lloyd's already talked about that. So that is so there. Yeah. Go to robothon.org and you can sign up there. It sounds like there may be a couple of slots yet for this August meeting or this August presentation. So do that. And after this meeting, we'll kind of leave the Zoom meeting running, but won't record anything. But we can just have general discussions for anybody that wants to hang out, and kind of like what we used to have in our in-person meetings. There after the meetings, you just gather and chat. Okay, so at this point, I am going to open the floor for general sharing. People have brief sorts of things. We'll do our formal presentation after all of this and a short break. So at this point, this is going to be pretty much everything but our actual presenter, unless of course he has something that just in general, perhaps of general interest to the group that he would like to share. Everybody is welcome to jump in. Several people had contacted me regarding, let's see, sort of some special announcements that they wanted to make. So if they are online, why don't you go ahead and just take the floor. If there's anybody there.
Yeah, I have one. If it's allowable. We'll put that. So,
all right, I'll get my finger on the mute button so I can
yeah, definitely get ready to mute me. No, I just won't share if you don't want me to. So, we have a meeting with the group up north in Snohomish County, and we're changing our meetings, to, well, I mean, they're staying on the same date, but we're changing our format a little bit, and starting in 2 weeks, next meeting, we're going to run 6-month challenges for low barrier robotics challenges. They're not competitions. It's just a challenge against the challenge itself. And our meetings are going to have mentoring built into every single one of our monthly meetings. So our first challenge, I have a little website. If it's allowable to share, I can just throw it in the chat, but it's
absolutely.
It's a rope climbing challenge. It's something you could build out of cardboard, or if you're, super into it, you could CAD it up and build circuit boards or whatever you want. So real low barrier. And I'll share the, Mitch, they are virtual. They're on the Snowco Robotics group. So, and we have some information that you could find through the link. I'll just drop that link here in a second.
Yeah, drop everything into the chat. That would be helpful.
So there's the description there in the chat of the challenge, but we are going to start on that 1st June. I think it's 3rd or whatever the first Saturday is. That's when we meet. And yep. So
cool. Yeah. So the mentoring along with the challenge, that sounds wonderful. That should be good.
Yeah, if you run out of people that don't have anything to talk about, we can talk about a little bit more in depth, but I want to make sure other people have a chance to share their stuff too. Okay.
Yeah, maybe just kind of put a pin in that for a moment and see if anybody else has something that they would like to share.
Well done.
You got anything for us this month, Greg, with your arm? Or one of those other interesting things that you've been working on?
Here, unmute. So I put this diagram together. This shows all of the microcomputers and microcontrollers that are in Gidget at this point, or plan to be in Gidget. Up at the top up here, these are all the ones that are in the RoboBus card. Then there's others that are connected to the CAN network. And I put this together in part because I've added a few more in the ARM. So the controller for the ARM is a two-board combination, one that drives the stepper motors and one that is kind of the brains of the ARM. And then there's a number of boards, microcontrollers in the ARM at each of the joints. There's one up at the wrist that controls a couple things, has a couple sensors on it. And then each of the end effectors, the gripper, for example, has will have a controller on it. So the fat black line is CAN. So all of those communicate over CAN. There's a couple instances where UART connections are used. And then the thin black line is Dallas one wire. That's allowing the ARM controller to query the different sensors in the ARM. I've gotten the ARM moving to a certain degree. I just recently soldered up this controller card. So I've been driving the ARM with just the driver. Added to that code the ability to connect over the USB serial and kind of command it to do one thing or another. I have one other thing to share if it allows me to. Just a second.
Greg, I have a question for you on your ARM.
Yes.
Have you put together any kind of inverse kinematics controller?
This is version 3 of the ARM. In the first version of the ARM, I did have code written that would allow me to specify an XYZ location, and it would calculate all the angles and move the ARM there. I need to copy that code over. That is likely to be done in the controller. I haven't quite figured out how the workload is going to be split between the controller and the driver. That's still something I'm noodling in my head. But chances are that calculation will be done in the controller, and then the controller will send joint angles to the driver board. But that may change. But yes, I have that worked out. What I have to share is a couple short videos. And let me see if I can get those to come up. Just a moment here. And these are a month ago and a couple weeks ago. So, okay, we'll just do the whole desktop, I guess. Whoops, no, I guess we won't. Okay, no, it's not going to let me share. So I'll just put, I'll put the links to these YouTube videos in the chat.
Okay.
And when you watch these YouTube videos, you'll hear a clicking sound. That is the springs that I use to offset the weight. I've added some bushing, so it now does not make that clicking sound. YouTube. Okay, so I put one of the ones in there. Maybe Steve, you could share
All right, let me
those videos.
let me try.
They're not very long. They're like 15, 20 seconds. So
Oh, okay. Oops, no, I don't want to do that. Let me see here. Tab.
and so I'm at the point now, like I said, I've soldered together and have started coding for the controller card. Actually, this diagram I have behind me, I get to add one more box to it because I recently realized that I needed to have a little sensor for kind of like a homing switch. And I made a design change after I fabricated those controller boards. So I don't really have anywhere to plug that sensor in. And then I realized, well, I could use Dallas One wire if I put a microcontroller along with that sensor. And so I've written some code for another microcontroller. So I get to put one more box on my diagram.
Okay. All right. Let's see here. Figure out how I want to try to do this.
So right now another thing that I did do is I finally put the coupler connector into the coupler at the end of the arm and integrated a slip ring. I'd never used slip rings before. So now there's a slip ring in the wrist so that it can do continuous rotation if I find, I ever need to put a light bulb in. And so I'm cleaning up wiring and doing some wire management and doing those things.
Have you done any tests with COM through your slip ring?
Not yet. I did just get from a JLC PCB the board that goes at the wrist. So there's a board at the wrist that it's connected to the Hall sensor, which acts as a homing sensor for that rotation on the wrist. It's connected to the coupler, the electrical contact coupler has a couple contacts that it can use to confirm that the coupler is connected properly. So it connects to that. It also drives the solenoid in the wrist or in the coupler that allows it to unlock the coupler. So, and then kind of its fourth purpose is to give me a place to solder those wires from the slip ring, because there's a bunch of gears and belts right in that vicinity. I was worried that things might get tangled up. So by having that board there and having the wires come out of the slip ring right into that board, then there's no slack that can get tangled into things. So that's this weekend's project, is soldering that board up and getting the slip ring hooked onto it and so on. And then I'll be able to actually evaluate whether the slip ring is going to give me trouble or not.
Are you going to try to run one wire through that, or is
yes?
That, gotcha.
And I upgraded from a 6-wire to an 8-wire slip ring. So I have 2 conductors for ground, 2 for positive, and 2 for 1 wire.
Cool.
And so I don't know if people saw the new gripper. So here is here is the gripper that I was working on. Just like, let me turn off the background so the thing doesn't disappear. So here is the gripper that I had been working on for a while. And as much as I like the design and I really love the organic nature of how it wraps around things, I felt like it needed some more work. And it was one of the first complex things that I modeled. So the model in Fusion 360 is, it's not done very well. It's not very constrained because I didn't appreciate the value of having things constrained. And if you change anything, it just kind of blows up. So I'm tabling that for now. And the current more task specific gripper is this one. It's servo driven. It's got 2 fingers, obviously designed to fit a can. Without the glove fingers, the PLA is too slippery to pick up a can. With the glove fingers, I can pick up and shake a can. So that works out real well. And then you can see here, looking through the acrylic in the back, you can see the connector for the coupler there. And behind it is the circuit board that drives the servo, as well as right up here, you can see this little window, and inside there will be one of those little time of flight sensors, so that it can detect how far away the can is, and hopefully, get kind of a confirmation that the can is close enough to grab it. That little board also has a current sensor on it. So in theory, it could also monitor the servo current and kind of confirm that the servo has grabbed the can by watching the current go up. So, and then of course it communicates with that over one wire. One mistake I made previously when I set this up, I had a hole here in the side where I could put the ISP programming cable in so that I could update the code on that. And then I thought, oh, wait, I could just cut a hole in this acrylic. And you can see there's a 6-pin plug inside there. And I can just program it that way. That'll be cool. Just uncouple it and hook it on. But then I came to find out that I couldn't keep it hooked on and have it connected to the coupler for testing. So that's turned in kind of a nuisance, but. Did you get that video?
I think so. Yeah. Let me see what I can do here. So. Oh, okay. Cancel out of that. So if I do this one, those things are kind of being kind of persnickety down here. Let's see. All right, let me get back to. All right. Share. Huh. Wait a second. I guess that's where I want to share. And go to that one. There we go. Okay, I've got it. I just have the audio muted.
No, that's okay. I don't say anything.
Yeah.
So this video is it's just exercising the arm, just having it go through some motions. It does have acceleration and deceleration there. And it's set up so that it commands, it calculates the motion, the angle, or there's a destination angle for each of the joints. And so then it calculates the steps required by each of the motors to get there, and then determines which one's going to take the longest, and then scales the speed on all the others so that that motion ends, you know, so that all of the motors stop at roughly the same time.
Okay. And then this one.
And so this one is showing it's going out, it's able to couple and pick up the tool and then detach and pull back. I cheated a little bit there in that it's not engaging the lock pin because I don't have the solenoid being driven. You know, the solenoid wasn't hooked up to anything at that point. So I didn't try to move it around after it picked it up for fear that the gripper would fall off. But and it's got a differential wrist. I thought factoring in the rotation of the wrist was going to be a real challenge. Turned out to be very simple to factor that in to the motion calculations.
Cool.
Now,
Very nice.
all of this
Very
was
nice.
done. All of that was done by me through trial and error, figuring out what each angle needed to be at kind of each waypoint, right? So it moves so that the coupler is in front of the tool, then it moves it in, and then it rotates, and then it picks it up. So at each of those stops, I would, through trial and error, just kind of keep moving the arm by commanding each joint to go to a certain number of degrees. Once I got it to the point I wanted, I'd write those degrees down, then go to the next one and so on. And then in the code, I would there's a little motion cue where I'm able to put in, okay, go to these degrees, and then go to these degrees and so on. Ultimately, that's not how I'm going to be moving it or how the robot's going to be moving it, but that was where I was at that point.
Okay. Okay. All right. Thank you, Greg.
Yep.
Let's see. We got anybody else? There was I don't see her here. It was a gal named Donna, not our Donna, but a different Donna who was wanted to thought I invited her to join us here this morning. I don't see her on the list, so I'm guessing that maybe she couldn't make it for whatever reason. Okay. Anybody else got something that's just burning to be shared?
I just have another question for Greg, because I'm trying to build an arm, but I'm using ROS. Have you looked at the ROS Smooth It type functions? Okay.
No, I haven't. I have no ROS experience.
Yeah, I don't have much, and that's not helping, let me tell you.
Okay. Anybody else? Let's see, billing. I was pretty excited about. Oh, okay. See, there's Kevin just posted a note in the chat there. let's see here. Got my, get that one out of the way. Yeah, there, cool. Let me see. I have get back to sharing that one. Come on. Well, that's kind of annoying. Everybody, okay, there it comes. Boy, that was, man, that was painfully slow. Okay, before I forget, I usually end up kind of moving past this this slide before I intend to, and I just wanted to, you know, this is just a reminder for everyone, you know, same Zoom link next month. You know, I'll reach out to Kevin Ross, find out whether or not there's any chance we might actually have a physical in-person meeting. You know, I'll try to get the recordings up on the website here sometime this coming week, and do put stuff plenty, you know, just keep loading up the chat. It's always good. There's plenty of room in there. And let's see, it's about 1:45. I think we will we'll go ahead and start our break here, and I'm going to usually, let's make it about 10 minutes. So I got 10:42, so let's call it maybe 10:50 or so that we'll resume. And I would like to say, Kevin, why don't you unmute for a moment here, and I would hi, welcome.
Hi, thank you. Can you hear me okay?
Yeah. Why don't you just go ahead and pop up your initial screen there. Go ahead and share your initial screen, and just make sure that that's all good. And everybody, it's a good opportunity to run to the restroom or grab a cup of coffee or whatever here. And so we'll give us a few minutes to kind of regroup.
I'm gonna need you to stop screen sharing. It doesn't let me until I don't have the authority to take over. No problem.
Oh yes, yeah, that's right. I forget about that.
That's a good feature. You don't want someone wrestling it away from you in the middle.
Yeah, I suppose you're right. Okay, there you go. That should work for you now.
Okay,
I'm going to go ahead.
Should work okay.
Yeah, I am going to just since there's really nothing happening for the next 10 minutes here, I am going to go ahead and pause the video, and I do need to make sure that I restart it again. I'll try to be very intentional about that. In fact, I'll put a note right here in front of my computer to remind me to do that. So
this meeting is being recorded.
And today we have our special guest. Let's see. Let me get to my notes here. All right, come on. There we go. Come on. Our special guest today is Kevin Green, who's a PhD student at Oregon State University. And he's, let's see, member of the Dynamic Robotics Lab. And he studies modeling, control, motion planning as applied to legged robots. And his research generally focuses on robust and agile bipedal locomotion, particularly applied to the agility robotics Cassie Robot. And I'm sure we'll learn all about her today. Thank you for joining us this morning, Kevin. And I will turn it over to you.
Thank you. Yeah, thanks a lot for having me. It's always really exciting to share the kind of work we've been doing among people from all over, either in industry, research, or hobbyists, or all kinds of spaces. So I think, as probably many of you are aware, being robotics enthusiasts, we've seen an absolute explosion of legged robots out there in the past I think really over the last like 5 years, it went from Boston Dynamics had a few to it seems like there are dozens of companies making these things now. So here's a collection of these quadruped robots that became very, very popular. So, Boston Dynamics Spot, one of the earliest to the top left. You got MIT's Mini Cheetah, which did some really amazing backflips and things like that. Unitree, which is a Chinese company, made this really interesting robot. Ghost Robotics was a UPenn startup that now has gone full military contractor route, it seems like. And there's where they put a sniper rifle unit on the back, which has been caused a lot of discussion, at least within the research community. And then Antibiotics, a European company, they're from Zurich, Switzerland. They're really targeting, I think, oil wells. So off like deep water oil fields where you want to be monitoring a lot of things. Having an autonomous robot to be able to go and inspect the machinery is really useful because it's really hard to get people who want to spend a month off on an oil rig. So there's a lot of stuff in the quadrupeds, and those are really getting out in the real world, which is really exciting. We also have quite a few dynamic bipeds that are out there now. So starting on the left, we got Apptronic. That's a University of Texas startup, was where they came out of. Boston Dynamics Atlas is sort of one of the most well-known between dancing and just absolutely athletic feats. And then there's the two agility robotics. So in the more middle, that's the Cassie Robot. That's actually ours. That's the one I work with quite a bit. And then there's sort of the evolution of it, the Digit Robot, which is basically just the Cassie legs and then with upper bodies and perception stacks. And there's actually one other company that's trying to enter the bipedal space, and this is the Tesla bot, or so they announced. Clearly, this is a person in a suit, not a robot. But once they actually have and show a robot, I can replace this. But we'll see when that comes around. They said we should get it this year, but we'll see. So this is backing up. Like legs are really hard. Why would we even want to do this, right? Wheels are so, they're much, much easier. They're much, much more efficient, right? Cars go way farther on way less energy. And the idea is really that we have rough terrain, or we have like stairs, or we design the entire world around bipedal locomotion, right? The entire world is designed so humans can get around. So it's really natural. If we can do that, it would make a lot of sense. And they can be pretty efficient, right? Humans are actually quite energy efficient in this large scheme of things. And when you do locomotion well, it can be quite efficient. Granted, bicycles would blow humans out of the water, but legs are actually pretty good. And the other things, they're just awesome. They are really cool. Like, I feel like it's like one of the tenets of like really awesome robots moving around the world fluidly, and legs really fit in there in a strong way. But there are a lot of problems with them, which is why you don't see them everywhere. They're really complex, and that means they are expensive. There aren't really cheap, high-performance leg robots, at least maybe not yet. They're really much more difficult to plan and control compared to like a wheel or a tread robot. And then you have this problem that when you're moving well, you are unstable. If you stop, you're falling over. You need to actively be balancing as you move, even with quadrupeds as they get to their more efficient and agile gaits. And then you also do have a lower top speed. Like, that is a limitation, right? Wheeled robots, you can get up to highway speeds, or quadricopters, you see them accelerating to 200 kilometers an hour out of nowhere with some of these really high speed ones. But, legged robots, especially general purpose ones, you're not going to get much above, but 10 miles an hour would be amazing, but that's getting really pretty quick.
So
and the other thing is,
I have a question for you, Kevin. So the direction that the knees bend forward versus backward, are you going to kind of address that later on?
Yeah. The first May session, we're going to get into sort of I'm going to go through the whole hardware and software stacks and talk a bit about the kinematics and why they're done that way.
Okay, thank you.
And the other is that honestly, like, this is a bigger thing as these companies try to deploy these. The social interaction with these is very different compared to a self-driving car or one of these like 6-wheel delivery robots. I think it's a really interesting area that we haven't looked into quite enough, but it's going to be super important in the coming 5 years or so. So the rough outline I want to talk about today, I might skip over some of these to get to the more exciting parts. Starting with just going over the hardware and software stacks we use, talk a bit about reinforcement learning. I have 3 examples of different reinforcement learning things we've done. The very first one we did, walking like a spring, and then how we actually scaled stairs with vision. And then I have a couple, 2 or 3 really kind of interesting failure stories of, bugs or issues we ran into. And it's one of them has try to give you guys a brain teaser. So talking a bit about the hardware and software, I think this group will find this pretty interesting. Yeah, so here's our Cassie Robot. So it is a biped, right? You can see that. And there are 10 motors per leg. And here's the leg mechanism. So it's actually this closed kinematic loop. So if you think about it, it really is a parallel 4-bar linkage is what's going on with this leg mechanism. So I can label real quick the motors. So you have in the sagittal plane, starting from let's go the bottom up. Where's my pointer? Here we go. So down here, there's a linkage here that drives the foot, and that allows us to shift the center of pressure back and forth. So we have a little motor there. These are totally passive. There are no motors in this area. And then we have a knee motor here. So we call this the knee, actually. If you think of like extending your foot, this whole thing is basically the foot. This is the toe. Then your knee will extend this whole linkage out when you apply torque there. Then we have a hip motor, which can swing the entire leg in that plane. And there's 2 more motors up here that allow us to adjust the toe in and out and abduct the leg laterally. So we end up with 5 actuated degrees of freedom on this leg. And the cool part is that other than this toe motor right here, all the motors are really high on the leg. So it's a very low inertia leg. So you can swing it pretty quick. When you impact the ground, you have a lot of, you don't have that much mass you have to deal with. But the other really interesting thing is it's actually compliant. So there's actually 2 passive springs in this leg mechanism. So right here, this is a bushing, and this is a fiberglass rod or a fiberglass, think like an archery bow that will bend as you load it up, kind of like a tendon will in a human leg. And this back here is also a flexible rod that will bend and absorb some energy and impacts. And they're relatively stiff, but having that little bit of compliance helps a lot in preserving the transmissions. Yeah, those joints. And so we have there's 10 brushless DC motors through this. We have encoders on each of the motors and on the knee spring, along with an IMU on the pelvis. It's powered by a custom lithium-ion battery pack running at 48 volts. And that gives us enough power to do over an hour of pretty high-speed walking on this robot. Total weight, roughly 30 kilograms or 60 to 70 pounds. And we can get it up to about 4 meters per second, which is the equivalent of running a sub 7-minute mile if you did that for, a mile continuously. And when you're running, you draw between about 50 and 100 watts. And one thing I didn't have on notes, but the transmission designs are actually pretty interesting, is that they're really, really low gear ratios. I think that's a really important part of the mechanics of our robot. So the ones on the knee and hip here, these axes, they are only 16-to-1 gear reductions. And the idea of that is that you really want to be back drivable so that when you run across a step up or a step down or an impact with the ground, you're not going to have this giant amount of inertia and this big shock on your leg as if you had a really big gear ratio. Yeah, see a comment there. And actually the name Cassie, it comes from cassowary, which is kind of like an ostrich or an emu or like a chicken leg, because it was designed based on sort of math of inertia properties, but it ended up being almost identical to the topology of what you see in these large flightless birds. All right. So going on to the actual electronics chain. So at the low level, we have some commercial brushless DC motor amplifiers, and then some sensors, encoders, we have reed switches to zero the joints. And what we have is we have all these on these sort of a whole string of daughter boards on an EtherCAT bus. So here's one of them. This is actually on the pelvis. So it uses Ethernet cables. One of these is unplugged, but Ethernet cables to chain one board to the next, to the next, to the next. And that sends all of the commands, all the state information back and forth. And then they have lots of breakouts. So this one has read switches. I think this is the radio, because we use just an off-the-shelf, like a FR Sky radio to control it. And then there's like power. There's some logic signals that go on to different ones, depending on which joint it is. We have a whole chain of these. And I don't actually know much about the microcontroller firmware on these. I know it works, and I know it gives me the data I need out of it. Then that connects then back to, we have a real-time computer that's running a compiled Simulink real-time OS image. So that's a specially designed operating system to make sure it runs at 2000 Hertz locked solid. So that does a lot of that does sort of basic sensor filtering, some state estimation things to give us a good estimate of the overall robot pose. And it can do some locomotion control, but for our work, we generally just have that run joint proportional derivative PD controllers on each joint. And that gives us a lot of a really clean interface for what we want to do. And you go a little bit higher up, then we have a second computer. So this is all on the robot. There's a second computer, also these Intel NUC size boards, and it's running just an off-the-shelf, GUI-less Debian. So just like Ubuntu, basically. And from that, just whatever we want to run. For a lot of our learned stuff, we use just a Python script. And it truly is a Python script with some pretty efficient libraries. And then some earlier work, we were running like multi-threaded C++, some more intense optimization-based things. So yeah, the communication protocol on the Ethernet. So this is a custom just UDP messages. Pretty standard. So TCP/IP is one option. UDP is just a much simpler one. And when it's just going one computer to another, that gets us a lot of the way there for between the real time and the user. And so EtherCAT is its own protocol. It really is a lot like CAN, but it uses a lot of the wrappers of Ethernet and some of the other protocols. It's sort of built up. It's very common, I think, in industrial settings. You see, it's a little weird to see it in this context, just because usually you connect whole arms to each other for a whole assembly line. That's where it's sort of most commonly used. But it has some really nice properties and has really, really low latency in that, like, the latency when it goes from one board to the next, and like each board will populate its data on that message structure. It's really, really quite nice. Oh, here's a photo. So this is the back of the robot. So there's a plate taken off right here. That was where that medulla board we just saw was. And underneath it, there's one of the computers and another one of the computers. And so these are all powered by the onboard battery. They're all doing onboard computation. Yeah. And why do we do PD? We're going to talk a little bit about why PD makes a lot of sense. The real thing is that it has to do with state. So PD is really nice because if you try to figure out how you go from the state of my robot to what torque I'm going to apply, PD is just based on the positions and the velocities of your robot state. If you add the integral term, you have now added you can think of it like it's the integral of position. So if you have like acceleration, velocity, position, you now added this like hyper position, right? The integral of error over time, which is really powerful if you're trying to drive a steady state error. But we have some more sophisticated systems above it that do the sort of accounting for how you fail to get to where you want to go. So yeah, it has a lot to do with sort of that internal state, because then we'd have to like consider how wound up is my integrator. But great question. And then the one other thing, so we have an offline software stack. So we use a lot, our whole trick for what we do is we do a lot of simulation and we train a lot of controllers in simulation. And so we need a really high fidelity simulator that's quite efficient. And so what we've come to use is this software called Majoko. It stands for Multi-Joint Dynamics with Contact. And so this is totally free now. It used to be paid software that was pretty expensive, which was really pretty obnoxious. It was bought by, I think it was one of the Google companies. I think it was DeepMind had bought it from the original developer. They've made it completely free to use, and it's in the process. It should be open sourced within the month, which is really exciting. And so here's our robot in that. But the real trick is with these simulators, that's everything you see, all the detail there, that's just a visual mesh. the rigid bodies of what it's actually calculating is equivalent to this here on the left. You can make, if you have a rigid body, you can represent it by just its principal axis of inertia, and that's really all that matters. It's kinematics, it's your inertia tensor, and that's pretty much all. So dynamically, the left is the true model of the robot. And then we have to have collision. And instead of using meshes for collision, which can get really computationally tricky, we use capsules. So in reality, the dynamic model of our robot is the left and the right used together. And then the meshes just make us happy because that's what we're used to seeing. And so what we have is we have this Majoko library, and then we wrap around it that same code that's running to do the state estimation. We can compile it just to a C function and use that as part of our extended simulator. And then what we have is then a reinforcement learning system in Python that talks through a C types interface to the simulator. And then we can use some really sort of pre-built, efficient, and slick libraries to do some of our deep learning. And that's basically our entire learning stack, basically. So all the like RL stuff, all is done in Python. All of the really important speed critical simulator stuff, we have C and C++ wrappers. And if you want to look around any of this, these are two separate repos on our GitHub page, just OSU DRL. Yeah, so I think that's most of our software stack. So I was going to get now to sort of our reinforcement learning stuff. So maybe any questions on this?
You mentioned 10 motors. Was that 10 motors per leg or 10 motors total?
10 motors total. So it's 5 per leg.
And at some point, not now, but maybe at the end, I'd love to hear if you were trying to simplify this, for a hobbyist, which of those motors could you do without? So.
Yeah, I'll think about it a little bit. I think in some ways, so those quadrupeds we all saw, those all have the really nice advantage that each of the legs has 3 motors only, because each point's basically a point foot. So you only move it in X, Y, and Z. Because we need to actually modify some more things about balancing with the feet, it's really hard to do less than 4, I would say, for this robot. You really need to be able to move the foot in X, Y, and Z to lift it up. And then you want to be able to modulate the center of pressure on the toes so you can balance and stand. So getting below 5 starts to get kind of tricky, because if you want to then turn, that 5th is kind of important.
Okay, thank you.
Yeah, well, we're going to talk about that. And we actually kind of end up with something that's a lot like integral control, but an extraordinarily complicated one through some like learned systems. I don't know if there's much in terms of 3-legged robots. It seems that the field really does like the idea of like bio-inspiration, that quadrupedal gross morphologies, they really like those. And bipeds seem to make a lot of sense, whether it's more extremely humanoid or these sort of more avian style legs, which you see a lot. All right. So let's get a little bit to how we sort of go about controlling these. So when we think about this in terms of reinforcement learning and not just robotics, this is the loop that RL is all built upon, is that you have some control policy. We call it the actor. The actor will choose an action that will manipulate the environment. It will move it forward, and it will produce a new state observation that you can then use to select future actions. So you have this loop where you just go back and forth and back and forth. And the key is you try to modify that control policy so it will maximize some reward function, so that, what action should I take? Well, it's the one that will give me the most total reward over the entirety of me doing a full rollout in the future. And so you can get really deep into like the optimizer, but it's not really that important. It makes the reward go higher. So anything that makes the reward higher, it'll try to do. But the really sort of powerful thing about this is it tries to maximize that reward, not just for one state or for one environment, but the entirety of it. So you can actually create distributions of environments. So we can say, you know, we create a model of our robot, but it's not perfect. We don't know the damping of and the friction models of our joints perfectly. So what you can do is you can randomize it. You can say you don't really know what it would be because, you know, as your oil warms up or your grease warms up, it'll change. So we can actually create some uncertainty in the environment. And what it will do is it'll try to maximize the average of what it will do in terms of the reward. And then, of course, we can feed in some motion commands, and that will allow us to do different sorts of behaviors all within one policy. And then this environment isn't just the simulator, it's all the things you build on top of this. The observers, if you do a low-level joint controller or even a higher level controller, you build on top of that. So let's look a little bit on how this actually worked for the first time we got this to run. So this is some work that was a little before my time with this collaboration between University of British Columbia and Oregon State. And let's see, I might jump around this video. That was good. So the whole idea of this is that we had some reference motions of the robot walking, and we used that as a big component of the reward to tell it how it should walk. And I was able to walk on varying ground. So I was talking about, you can't expect the ground is flat because you don't have external perception. You have to be able to do well on average. So the ground, here in this case, it's sort of bumps. There they messed around with some sensors, but it did pretty well. But the real interesting thing was that it actually was able to work on hardware. You know, it doesn't look amazing, but at this point, creating a neural network that made the thing balance was the first time we had ever seen anything like this. So it was super exciting. And so the two parts of this, I think there were really important things to make it work, were this reference trajectory. So you had a trajectory of what the motion roughly should look like, which is really important because if you don't have that, you get things like this. Let me see if one second. Optimize for video clip. If that's a little clearer. But you can see it's just vibrating the legs forward. And it's just sort of gliding across the ground, which is a kind of ridiculous way to locomote because we know that's not going to work on our robot. So by using that full trajectory, here, you actually can tell it nominally what does the gait look like. And the other thing we did was we seeded it so the initialized all around this cycle. If you see on the right, this is sort of a picture what it could look like because it gates you moving in a cyclic motion. So you seed it all around your gate cycle, and that ensures that you're able to learn how to converge back to it from lots of different states. And you don't have to figure out how to get all the way around it before you can actually learn some of the behavior away from your seed point. Let's see. Yeah. Answer some quick questions. So for varying environments, so if it can't sense the environment, it can only optimize to the average, or it's sort of like a weighted average of what it sees, so you can manipulate it a little. But if it can't sense it, it has to just think about the entire average of what it sees during training. And it's able to balance while standing still. With how we parameterize some of these learn controllers, they always step because we have clocks that tell it to keep taking footsteps. Yeah. So the other thing we talked about, so why PD as opposed to PID, but the real question is, why not just use motor torque directly, right? Because you think you have a PD controller in the middle, and if your neural network's just outputting some nonsense, it could just skip that and output the motor torque directly, right? You can always invert the PD controller if you know the state. So you could do it. And the real reasoning is there's two real things I think that matter quite a bit. One is that you run these at different rates. So the PD controller itself, we can run them at 2000 Hertz, which is basically continuous for all sorts of, real world situations. But we can run our neural network much, much slower. So 40 Hertz torque control, it's going to be ugly. That would not look very good. But updating the position commands for PD control at 40 Hertz is actually somewhat reasonable. And the other thing is, if you imagine what would a constant command look like, because a constant thing is easier to learn than a super varying reactive. A constant PD command is going to be roughly stable, and you can get a lot of different locations of, say, a single joint with a constant position command. If you give it a constant torque command, you're probably going to run into a joint limit if you leave it for long enough, because it's just going to diverge. If it's not strong enough to hold up the weight, it'll fall down. If it's too strong, it'll run into its other limit. Yeah, and there's some actual work where there's been a lot of the sort of this learning work has been done by animation communities. So you can see here, this is doing the exact same learning. This one's using a PD controller. This one's using a torque controller. And you can see it's not exactly a great motion out of the torque controller. And with the learning curves, PD learns very fast. Velocity space, so instead of commanding a position, you command a velocity. And then there's some other ones, torque and muscle units. So then there's a dog motion. And torque is losing its mind, where PD is doing pretty well. So this is some really interesting work. I think it really inspired a lot of how we started to look at these. So then building out, this is my work, walking like a spring. And the real interesting thing is this trajectory matching, it's really overspecified. So if you have a robot that's trying to walk over all kinds of interesting terrain, you're gonna have to change your actual body shape quite a bit. But one of the most important things about how you traverse is what is your center of mass doing? Because the center of mass motion is much smaller dimensional, so it's a really compact representation, but it really connects well with what your legs are doing. Because your legs apply forces to the ground, and the sum of those forces will tell you how your center of mass moves. And so if we think a lot about what should the center of mass do, we can not worry about all the complexities of our leg mechanics within reason, and that's a really compact way of describing a gait. And in some more classic leg locomotion things, you can model how humans walk pretty accurately with the center of mass, so a mass and a spring. So if you compare it here to the center of, or this is ground reaction forces plotted down here, we can see that for human running, the spring does a pretty good job, right? There's some interesting things here. This is toe off. And you can see it actually reproduces this, what we call double humped ground reaction forces during walking, where some other models don't quite represent so well. So with just a mass and a spring, you can reproduce a lot of the behaviors of human locomotion and also other animals' locomotion. And so what these sort of spring mass gaits look like is something like this. So what we thought to do is, what if we optimized walking motions, just nominal steady state walking at a bunch of different speeds for this sort of model, and then use that as the reference trajectory instead of some arbitrary full order one for the robot. And this actually worked really well. So looking here, we trained a controller, and now we're going to command at a bunch of different speeds, and it'll have to change. So the blue here is what we're commanding. That's like your joystick. Here's what that optimized body motion would do. So that's what the spring mass models are doing. And then here's what the actual robot does when we run it. So here we're walking around, takes a couple steps to speed up or slow down, but it's doing a pretty good job. It lags a little bit in speed. You can see the black lines at the higher speeds is a little bit below the blue on average. So it's not perfect at all, but I think it's really doing a pretty good job capturing these dynamics. And I think this is the part that really was saying to me, if you line up the reduced order model on the left, the controller in the, so the simulated one in the middle, and the real one on the right, we're getting a lot of that motion and the properties of the motion transferring. The body is oscillating side to side, up and down in a very similar way. Legs are moving in very similar ways. So we're definitely getting a lot of those dynamics carrying through. And we can do the speed changes on hardware. Speeding up. So here, so the shoulder pulls in case it falls, so we don't absolutely destroy the robot, because even though it's pretty nice hardware and we have funding, it really slows you down when you blow up a motor or crack something.
Full speed. Slowing down.
Yeah. Now I want to talk a little bit about how we walk up and down stairs. So this is work, it was led by Jonah Siekman, who now works for Agility Robotics, and along with John Warilla. It's a leg day for the robot, arm day for the handlers. If you try to catch the robot when it falls, you'll definitely get an arm workout, because trying to grab 30 kilograms as it's falling over is a little bit of weight there for you. So we thought about, we got some pretty good locomotion controllers, and they can take sort of small step ups and downs, but if you give them repeated ones, they are not able to handle that. And a huge part of environments, like, so on the left is Oregon State's campus, that's our mechanical engineering building. So you can see a load delivery robot, but that robot's not going up those stairs. And on the right is a trail off in, I think that's out in the Cascades in Oregon. And, you know, it's way off in the middle of nowhere, but we built stairs in so humans can get around. So being able to go up and down stairs is a pretty crucial part to navigating useful environments. And so what we thought is, you know, I'm not going to go running up to stairs and start climbing them without looking at them at all. So that's kind of ridiculous to expect our robot to do that, right? So what we did is we tried to think, okay, what's the smallest amount of information we can give this robot? And we thought, okay, you know, full RGB cameras, that's so much data, and that's, you know, big neural networks to deal with it. Let's go simple. Let's pretend we have a LiDAR or a set of time of flight sensors. And let's say we just have 6 of them that are fixed to the pelvis. We think that should be enough information to infer the shape of the stairs if you know they're going to be stairs. So we built that out. So you can see here in this video, we have these like rays that are sensing the distance, and they stop because they have a max distance. And we trained a walking controller that the idea was hopefully it will go up and down these stairs. And we found that we trained it and it worked. That's awesome. But there's one issue. We started looking back in the code and we realized we had a bug. And the bug was that we implemented these rangefinders, tested them, visualized them, but we didn't give them to the neural network. So we built out all this sensing simulation, and then we trained it and it didn't even need them. And it made no sense to us. How is that possibly true? How is it able to go up and down these stairs without seeing them at all? It kind of blew our mind. So we thought back to some of the other research. So we're friends with a bunch of biomechanists. And we thought, how do animals do this sorts of thing? And this, speaking of chicken, so these are guinea fowl actually. But there's a really, really interesting experiment here. So this was conducted by Monica Daly. And what it was is we have a narrow hallway that these guinea fowl, there's a grad student with a broom behind them, pushing them along, kind of prompting them to run. And what they have is there's a drop. And above the drop is tissue paper. And so when they try to step on this tissue paper, they're going to punch right through it. So what this allows them to check is, what does the guinea fowl do when it encounters a drop that it didn't expect? So you can see in this video, it's running along and the leg punches through the paper. And the body lowers, but it recovers pretty well. And one of the really interesting things to look at here is the leg angles of the bird over time. And specifically in this range, so the dark line is the drop step and the light line is if it was flat ground. And so what we can see is that the leg keeps swinging backwards. So it goes from 40 up to 80-ish in that time in between. The light dash line's level ground, the dark line is the drop step. And visualizing this a little more, what we can see is this leg angle is changing. And what this kind of allows you to do is you're allowed to pick what leg angle you would want given the height of the ground. So if this bird was completely blind and there was a step up, it would hit the ground with a very steep angle or maybe shallow angle. If it's level, it's sort of a normalish one. And if it's down, it's a much more vertical leg angle. So it's actually modulating the leg angle based on the height of the ground that it doesn't perceive just by swinging the leg, the fact that you're falling. So if you vary the leg angle over time, you get different leg angles as a function of height, which is a super powerful thing to create a robust locomotion. So this is our theory for how our robot's doing it. So we'll take a look to see if this actually makes any sense with the method it actually did. So to actually learn this, we take our standard reward, randomization, action, observation loops. And what we varied is just the distribution of ground. So instead of seeing flat ground or slight angles, we gave it these plateaus of stairs with random amounts of stairs, varying the height and dimensions of them a bit, and sort of these landing widths. And ground slope. Yeah, so this reward, so the rewards, it's usually a whole long function. Let me see if I have, I have some slides we'll get to, I think maybe after this one, I'll find some. The rewards are generally relatively simple. So a lot of it is, so for the first work, it was matching all of the joints and the pelvis sort of velocities. For the spring mass, it was just foot position. We actually looked at task-based performance of foot position and body positions. And then we always do things like we penalize high torques or rapidly changing PD commands. So we have some smoothing terms. So it's just quite a few terms, but none of them are that sort of that fancy or special. It is it's like joint deviations. We generally will do task-based. We call them body and feet because that's what we really care about. Good question, though. But then we take that, we train it, and we get out these very robust controllers. So once again, no cameras, no perception at all. You have a person with a controller that's giving it velocity commands. So it says go forward at so-and-so speed, turn at so-and-so degrees per second. I'm not sure if these have lateral walking too, but some. And yeah, that's an important key point. Because it can't see the stairs, it has no way of actually lining up 1 foot per stair. So we're gonna see it a bit here. There it kind of slipped. And coming down, it's about to skip a couple stairs. Just because there's no way of lining up. And yeah, it did step back. And I think I have a slow motion one right after this. And just because it's on in simulation, and if it falls over in simulation, it's 0 reward, it's really bad. It can learn to do things like catch itself, go back down the stairs. It'll trade off going forward reward with staying upright. And it's really amazing, these sort of emergent behaviors just from working a lot in simulation. So here's a really good one for the stepping backwards. So it's stepping up, gets 1 foot, great, 1 foot, great. That one, real solid. This one, it only gets to the front of the toe right there. And it tries to apply heel torque, doesn't get anything. It's not on the ground. So it steps backwards really competently, honestly. Gets its center of mass back ahead of the feet, gets that momentum going forward, and gets the rest of the way back up. And so all of that, deciding which step to step on, is fully emergent of our neural networks, which was really pretty amazing to us to see. But one interesting question then, going back to that leg strategy, is it doing that? Is it doing this sort of leg swing behavior? And we found it actually is. So this data, it looks really smooth, but this is real simulation data. And what we see here, when we trained it, so what we did is we kept everything the same. And for one of them, we trained it on our stair plateaus, and one of them we trained it on nominally flat ground with a little bit of noise. And the ones with stairs, we see this leg angle, it swings much further forward, and then it retracts at a faster rate than the flat ground. And we can label some points. So 0 is the level ground. This is the sort of the max step size step down we had. And this sort of resembles, the fact that there is this rate of change here, we saw it being more prominent. So it's not everything. There's lots and lots of things going on, but it's really cool to see what I would call biologically recognizable strategy. that just emerge out of some of these like simple reactions. Let me see. How can I get to my slide list? So one question about reward functions. So this is jumping back to the one with the spring mass. I have a slide for that reward function. So this is the entirety of the reward we used for it. So there were 5 terms. We always try to make it so the reward sums to a total of 0 to 1 per step. So basically 30% of it was making the center of mass velocity match. 30% of it was making the feet positions match, and that was feet relative to the body. 1 is a thing we call straight difference, which basically penalizes it for drifting too far left or right from the line of the direction it's supposed to move. We had 20% for the foot orientation, so it doesn't really sort of pigeon toe or duckbill its feet or keep them at really weird angles. And then 1 is this action difference, which is basically don't have your PD set points be super far apart. And that's the entirety of the reward signal. And the one thing to add on is that when you do learning, you also have termination. So if the robot falls over, we just stop simulating and we give it zeros for the rest of that sort of trial. Yeah. Okay, let me jump back now. Where was I? So now I think we're getting to just some sort of fun sort of war stories of working with the robot and some really interesting failure modes that we came across. This first one is going to be a bit of a brain teaser. So I'm going to show some videos and show some log data. I want to see if we can get any guesses as to what's going wrong here. Okay, so we're taking our robot out, just sort of running it around, trying to get higher speeds, and we notice these stutters. So there'll be some slow motion of it right here, I believe, where it's running along, and it just pauses for a second, and it keeps going. And these get worse over time, so the longer we run it, the worse these get until it eventually will always fall over. So it starts off great, you get them, they're pretty evenly spaced. Okay, so we got a guess, not quite. This video is actually really shaky, so I'm just gonna skip that one, but it's basically what's happening. So we look at the log data of what's going on, and we see something like this. So what we're doing, so this is the logged motor positions and motor torques of our robot. And we see a big empty section. And if you look in there, they're not actually constant values. There's just a big gap of logs. No? So one thing we can then look at the control, the timing of our loops. So how long does each control loop take? So here is as we trial. So 0 is when we first turn the robot on or start the controller. And we have the cycle number. So how many sort of control cycles have we gone? And we measure the time from the start of it to the end of it. And we see this. We see these periodic spikes where they take longer and longer up until eventually it's strong enough that the robot falls over. And every time we get one, it gets worse. Okay. So there's all the info now. So what can cause that? If you have guesses, you can unmute too. Error accumulation is getting kind of close. It's actually a much dumber, in my opinion, a much dumber error. It's a very much like a software bug itself. Nope. The state estimates are actually good. It's actually really time to overflow. It's getting pretty close, actually. No. Okay, so you guys are getting pretty close here. What it actually is, we created our log variables in a very, very dumb way. We were using a dynamically resizing array for the log data, and periodically it would need to expand the size. So it would double the size. So that's how like a C++ vector, the standard vector object, or arrays in Python by default work. As you add more data, it'll allocate a big chunk. And as you get close to filling it up, it'll basically double it. And so every time you want to add more memory, it takes a little bit longer for the OS when you ask for more memory. And we thought we had enough RAM, so just fill up a local thing, but we didn't pre-allocate a huge size of it or anything. So that's what it is. So it's basically our control loops are pausing to allocate more memory for logging data. And the way we fixed that is we spun up a second thread and then wrote to files periodically and just handed off blocks of memory, and it was no problem. But it's kind of funny that that ended up being really important, that extra lag of allocating a bunch more data. It's another interesting one. So we also did a 5K with a robot. So we ran for 5,000 meters. This was our first trial of it, which we failed, and we're about to show it failing here. But eventually we did it in 45 minutes and 53 minutes, one on a really nice surface and one through the actual streets of Corvallis. But the first one, we got maybe a couple hundred meters, and then this happened.
Yeah. Is this not working? This one works, but this one isn't? Oh, yeah, we've had issues
So,
with that before. Okay.
Walking along, and then it fell over. So what actually happened here? So we can kind of see here, what happened was the foot bolt that allowed the toe actuator to actuate it fell off. And so that rod was just sort of hanging and you had no actuation on the foot, which surprisingly, you can still walk okay. It's not as good, but it's somewhat okay. But the student who was operating it got really nervous when he saw a bolt fall off the robot. And so he shut off to safe torque, we call it, which is just shutting off the robot. And that caused it to then fall over. You know, we can put the bolt back in, not the end of the world. We should be able to just restart as long as, you know, nothing's actually really damaged, but it wouldn't boot. We tried to shut it off, restarted it, nothing. Couldn't get any signs of life. You know, it beeped or whatever, but, you know, it wouldn't actually post. So we took it back to the lab and we're like, what the heck? We started tearing things apart, part by part, and we found the failure. So this is inside one of those nucks. And if you see in there something that really doesn't belong, let me switch back from video to slightly better. So if you look in there, we have a nut that fell onto the RAM module. And so what this is a nut that was holding in like a fan. And the lesson here is use Nylox. It'll save you so much pain in the end. And the amazing thing is the computer was absolutely fine. I don't know how, very rarely in my experience, you be able to short pins and get away with it, but we were able to pull it off. I put it back on the test bench, ran a bunch of benchmarks, and it worked just fine. So count my lucky stars on that. All right. And then the third and last one I want to talk about here is this idea of impacts. So as you're walking, you slam your feet against the ground quite a bit. And if you want to figure out what's the best way to do it, I want to do it such that I have the lowest actual impact. So the actual impulse I feel, lower is probably better. It'll damage my robot less. And so if you think of where to apply an impact, if you land with a flat foot, you're basically going to apply it right to that center. But if you apply it to the heel or the toe, you think you should do a little better, right? That's why when you're running, when a human runs, you want to strike with the toe and the balls of your feet so that you have more joints to absorb the impulse, as opposed to heel striking, it'll go right up your shin. So we generally walk with a flat foot touchdown with our robot. So we thought, okay, let's try heel striking, right? Then we can hopefully reduce the impact. You can run sort of the rigid body math and it should work. And we tried that. And here's a policy that heel strikes. Let me switch back to the optimize for video. So here, hope you can see that. You see it's striking pretty clear at the heel of the foot each time. But it turns out that was a really, really bad idea. And the reasoning is, it's not just how big is the impact, it's where's that impact going. And on our robot, that foot actuation is not very compliant. So we see here, we cracked the crank that was driving the foot using that policy. Then we also sheared this rod completely off and wore this foot away through the rubber down to the aluminum, which these things weren't, I mean, we break rods occasionally, but this was all in one day's trial using that policy. It was not very good. So it's kind of interesting that even though the math, you can do all the math you want, you can simulate it all you want. If your robot isn't designed around that, you're going to have problems. So there's a lot more complexity to hardware than a simulator will tell you, or than a rigid body, than what the fancy correct math tells you. So there's a lot of things to interact, I guess, in getting to that. All right. I think that's about all I have. Hopefully I left enough time to have some interesting discussions. I want to thank everyone from my research lab. Here's just some. There's more that I think I left off. Different grad students I've worked with over my time, and professors, particularly Alan Fern, Ross Haddon, and Jonathan Hurst, who've mentored me over the last 5 years. Well, I've gotten to play with the robots and learn a heck of a lot. So also, any questions I missed along the way, feel free to bring them back or to unmute. And
how much longer till you're done with your PhD?
Hopefully about a month till my defense.
Oh wow! Oh, we just caught you then.
Yeah, right at the end, hopefully.
Yeah.
Well, yeah, still figuring out exactly what's next. I was leaning towards the academic path. I went through job searches for professorships, got pretty close on some, but I think I'm going to end up doing a postdoc to learn a little bit more. So PhD program, unlike sort of undergrad degrees, the classes are one part of it, but your thesis and your contribution to research is a huge part of it. And the defense is basically you come in, you present all of your work that you've done over or sort of your thesis really, which is the summary of the important work you've done. And you present it to a panel of, I have about, I think 5 professors on the panel, or they don't have to be professors, they can be PhDs in general, but who will sort of judge whether, you've done enough to receive a PhD. And it's a little adversarial, but it's usually not too. They want to make sure you're ready, but yeah, that's sort of what a defense is.
So in terms of your strengths as you think about robotics, you've got electronic, you've got mechanical, you've got software. Are you pretty well rounded in all those areas, or is there any particular area that you're more, just say where your strengths lie?
Yeah, so my background was mechanical engineering originally. So that was what I studied through undergrad. And that's, I think, the perspective I come. So I don't know if it may have came through. I really think about the dynamics first, and then the software required to actually get it to behave properly. A lot of it's implementation, which I kind of enjoy, but the perspective I come at it is the dynamics of it.
Okay, looks like
you got a question here. Does a policy learned in simulation translate directly on boot up? Yeah. So there is no on hardware learning. All of these neural network policies, we learn them in simulation, and then we take it and just drop it on the robot and cross our fingers. And we do iterations because they don't work quite a lot. And you have to figure out why they didn't work, what we can do better. Yeah. So sometimes it's called zero-shot learning. There's a lot of different concepts or different terms for these sorts of things. I would love to do more online iterations. That starts to get really hard because sensing is hard enough to do control, let alone evaluating how good you did. And the other thing is the amount of data we need. So our simulator, I don't know if I mentioned this. So if you run it, the whole simulation stack from running the neural network down through sensors and the physics simulation, on like a good desktop, we can run that about 2.5 times real-time speed on a single thread. But we do all of our training on servers, which are big multi-parallel ones. So when you do all the parallelization and you do the optimization, which is a hard step of the neural networks, we end up collecting experience at about 25 times real-time. So these things take about a day or two to train oftentimes, which is equivalent to about a month of continuous walking experience for the robot, which would be really hard to get on hardware because you're going to break your robot well beyond you get enough, at least if you use these sort of very naive. You can do higher things. Let's see. Lovish, you have a question?
Yeah, I've got another one there.
Hey, Kevin. Thanks. I think this was very informative presentation.
Thank you.
I have a 12-year kid, and he's very much excited to learn robotics. But when I try to see like how he can start learning, because like these things are pretty costly too, right? Getting all the hardware. So do you have any suggestions how he should start? I saw like Vex is there, Lego is there. They have some leagues going on. But do you have any suggestions, or you have any classes which?
Yeah. So I mean, my first experience, I can talk about my personal one. I was involved in a bot ball league, it's called. I'm not sure if it's still running, but it's a lot like First Robotics or Vex. But the part that really got me excited about it was it's fully autonomous.
Okay.
Which is because I feel like in some ways, First Robotics is really a hardware first competition, right?
Mm-hmm.
So much teleop, which is really cool. It's great. But I think within the like sensing and sort of that control, think, act, reaction loop, and seeing you build a thing and it goes and just works on its own, that was always a really cool thing to see.
Mm-hmm.
So that sort of thing was fun. And I think having that structure, because I know as a kid, I had a short attention span. So personal projects that were fully my own were a little bit tough, but having some structure of a group helped quite a bit.
So what is the name you said? Can you repeat again?
It's called Botball. BOTBAL.
BOTBAIL. Okay. Okay, cool. Thank you.
So that's at least my path. I'm sure there are lots and lots of ones.
Okay. Thank you.
So a question here from Jesse then. Other simulation software. This is a space that academics love to spend their time arguing about which simulator is best or which one's right or which one should you use. So Majoko is one of the really popular ones. Another really big one is called Bullet or PyBullet, depending on if you use the C interfaces or the Python interface. And it's a good software. There's some slightly different features in them that matter. Majoko, so when you dig down into the algorithms for simulating rigid body trees, if you have a closed kinematic loop, that gets quite hard to deal with. You have to do a bunch of pretty fancy math to close a chain. So if you do parallel linkages or things, if you want to simulate those, it's a lot harder than just doing a forward chain like most, let's say, robot arms generally use. And Majoko really handles contact in a nice way. It's, in my mind, pretty easy to work with. Dojo is a new one. I've been looking at this a little bit. Dojo's interesting. It's in Julia, which is a big up and coming sort of, a lot of mathematicians really like Dojo. Looking into that a bit. NVIDIA is doing some really interesting GPU simulation. There's a lot of options out there, and I think most of them are pretty similar. The rigid body dynamics are all going to be correct. The contact modeling is the like tricky part that a lot of them, they say they're doing clever things in that space. But my opinion is that the real world has so much variability that as long as you can vary properties of your simulation, you're probably gonna have a pretty good time. Yeah, that's a good question there. Let me go back. So I guess I skipped over this a little bit. So the architecture of these neural networks matters quite a bit. So we talk about the integral portion of it. These control policies, so we talk about first a standard neural network. You take the input, which is sort of like some vector. So you have, like 60 numbers, and it will then just map it to, in our case, 10 outputs, which are the 10 motor targets. What you can do with this, instead of just doing a forward mapping, is you can make it based on the previous state as well. So we call that recurrence. So a feed forward is only using the current state estimate. A recurrent network can use its previous states. So you see, I don't know if you can tell in here, we have these little loops in this diagram. That's supposed to indicate that there's internal recurrence. So each node of this neural network can also look at its past value. And so what we've found in some of this is that they actually can observe what's happening in the dynamics of the system and sort of act like an integral term. And the difference is we have 500 integral terms and we have no idea what they're doing, but they make the robot walk good. And that's really how black box learning kind of acts. Yeah, thanks for bringing that back up. I want to touch on that.
How do you come up with all the terms for the neural network?
Like the internal weights, or like
well, you said there were
structure?
500 terms there. Not really. I've never messed with them.
So it has to do with the sizing of it. So if you think about it, so I think this diagram to me shows it pretty well. You have these circles here on the left are, say, the inputs. So that's sort of the descriptions of state. So if you had a robot arm with like 3 degrees of freedom, you might have 6 of them for the current positions and velocities, maybe.
Mm-hmm.
And maybe you have a couple more for where maybe the X, Y, Z of where you're trying to go, just as a sort of rough example. So you have something like 9 inputs. And then the output, it's where are you going to actually output? So this might be 3 deltas for your PD target locations. It's a pretty common thing. So what direction will you move within joint space? But then the question is, you have these internal ones. And the power of neural networks, they're called deep neural networks, is you have these, they call them neurons in between, which are layers that have some nonlinearity. And the dimension of these gives you sort of the size of it. So in ours, when we do it, this is roughly 60-ish dimensional, depends on the project and the sort of user motion command size, and then 10. But then we have 256 neurons in this first layer and 256 in this layer. And when you're using what we call recurrent networks, each of those not only sort of does some computation, they also look at their previous state. It's called long short-term memory, LSTM, which that's getting way deep into these things. But in the answer, though, coming back to this, the size is, I don't know, you just play around with it. You run it a bunch, you see you want it to be big enough and no bigger, right? Because as you get bigger and bigger, your parameters get gigantic. So it's kind of a balance. The smallest we've ever gotten, you did some really aggressive kind of goofy things, but we got a 16 by 16. So 16 neurons and 16 neurons, which is teeny. It's amazing that was enough. But generally 64, 128. We generally do powers of 2 because computers like that.
Is there a good place to start, like looking into neural network stuff outside of very rigorous academic setting?
I think one of the best places, OpenAI's gym environments, they have a lot of different sort of, they're off-the-shelf simulators all built. You have nice interfaces for this action state loops, and they have example implementation of the algorithms, and you can start tuning and playing around with the neural networks. So the real key to these is, using the libraries available. So we use PyTorch for Python. TensorFlow is a good one for C++. I think even MATLAB has a bunch of deep learning stuff in it. But yeah, so I think sort of building off of it, just sort of playing with the knobs. The one kind of annoying thing with them and sort of like messing with them is that they take quite a while to train. Like they're fast, but for what they're able to do. But compared to like running an optimization type code, which do some more, or just running a single simulation of a controller, they're pretty slow. Yeah, in some ways, the academic stuff gets really caught up in trying to prove properties or trying to like do some really like regret bounds and things, which you don't really need to get into it. And the funny thing, so the actual algorithm we use for this optimizer, so there's lots and lots of algorithms that everyone loves to talk about. And there's one really sort of well-known, extremely rigorous, but a real pain to implement. And that was called TRPO. Name doesn't really matter, but there's a rigorous one. And then someone created a really, really simple, rough approximation of it that has let's say someone was OpenAI created it. And there's not really guarantees, but like it intuitively makes some sense. And it's an order of magnitude easier to implement. And it tends to work better anyway. And so that's what everyone who does real hardware uses, called PPO, proximal policy optimization. So that's what everyone tends to use now, so it's an interesting back and forth between sort of the people trying to rigorously prove things and the people trying to get real robots to do real things. And there is some overlap, absolutely, but.
So I'm kind of interested in your sensor resolution. So in a lot of the control loops I've done, that seems to be a problem. You don't have enough sensor resolution to actually drive the controller properly, and it just kind of almost turns unstable. Not quite, but almost.
Mm-hmm.
So what kind of sensor resolution do you use on your joints?
Yeah, so how it works. So one of the things I think that helps quite a bit with this, the encoders are on the rotor side of the transmission.
Okay. So you get a little bit more movement.
So I mean, we have low transmission ratios, but you get, you know, a factor of 16 to maybe like 25-ish. And we use I think it's 12 or 13 bit encoders, absolute. Yeah. So absolute encoders, 12 or 13 bit. But we still run into problems. I think it's always a little hard to tell whether our problems are coming from loop delays or from sensor resolution, right? Because those both sort of fight against each other, and they both make it a hard time. So we see it mostly in our derivatives. So when we're doing, you know, velocity estimation, when we do our PD controllers, our derivative gains are, you know, about as high as we can run them where we run them. So there's still some loop delays you could probably get rid of if you wanted higher derivative gains. But yeah, that's a big part of it for sure. Okay. And I mean, the thing is, you need a good encoder on these motors. So that when they're brushless DC, we're doing field-oriented control in the, well, we're not, you know, the motor amplifier, the commercially available one is doing field-oriented control to get really good torque. But yeah, I've seen some pretty decent ones. But in that space, I don't know if you guys have ever heard of the O-Drive brushless DC amplifiers. They're really pretty slick. So it's sort of aimed at sort of high-end hobbyists. You can get a board that's about $200, and it will do 2 brushless DC motors, field-oriented control, and it will run local PD on them. And you can run some really awesome, compliant, good feedback. I picked up a couple during the pandemic just to play around with at home, and I was really impressed by these amplifiers. And they can get some real. I think they're coming out some even higher power ones that will drive like 40 amps continuous at 40 volts if you wanted something pretty wild. But I think a lot of it comes down to working with good brushless motors, and the amplifier technology has gotten really great.
Okay.
So I don't know if I got entirely to it, but that's the one interesting thing with our because we're on the rotor side. We have to home our joints when we start up because they don't know which revolution they're on.
Right.
So there's a couple of reed switches in some of the joints. So you have to collapse the leg mechanisms and like move it all around to calibrate the hips. And you can actually miscalibrate, and it'll walk sort of duck-billed or pigeon-toed if you miscalibrate them.
Well, it also seems like you could use something like a pot just to give you a rough position and then use the other.
Yeah, I believe on the digits now, they actually have encoders on both sides of the joints, so you don't have to do that.
Ah, okay.
And I don't know the accuracies of them all because I don't have a digit yet. Cool. Well, thanks so much for having me. So I actually am about to fly out to the ICRA conference in Philly. So I have a flight I need to catch in a couple hours, but yeah, thank you so much for having me. It's really great discussion. Some awesome questions.
Thank you so much for joining us. It was we really appreciate it. This was a fascinating presentation. If you don't mind, could you send me the slides?
Yeah, I can do that. They'll be a little big, so I'll probably share a Google Drive link. It might take me a day or two because I'm about to get going.
That's perfectly fine. Yeah, no big hurry. But yeah, this be fun to watch some of those videos again.
Yeah, absolutely.
Yeah.
All right.
All right. Well, thank you so much.
Take care.
Have a good flight. All right. Well, that was fun. Any post-presentation comments there? That was really cool.
Yeah, that was super neat. I really like that he was able to handle the integral portion kind of internally in the neural network. So it was pretty neat.
Yeah. Yeah, I was kind of thinking when he was talking about the robot stumbling, where they were out on the football field, I think, and the robot would run, and then he was talking about that problem that was actually, the way that they allocating memory, and I got to think of, I don't know if you've ever experienced this where you're like, you could be running along and it's almost like your body gets ahead of your brain, and you can trip and stumble. If you're running really hard and really fast, it's almost like you get your body can't stay in sync. And I was kind of thinking, well, it kind of sounds like maybe that's what's happening with the robot. I guess in a way that kind of was what was happening with it.
Yeah, just spaces out for a second.
Yeah. But that's pretty funny that it turned out to be something really silly like that. That's awesome.
The phrase I thought of that he didn't mention was garbage collection, but I don't know if that had anything to do with it specifically. But you usually, when you're doing something real time, you want to pre-allocate. You want to not do any garbage collection at all.
Exactly. Yeah, that's right.
Steve, I wanted to mention that when you walked away during the break before the presentation, we finally got a chance to see the punchline of the cartoon behind you. There had to be something besides the oxygen bottles and the little piece of paper, and it was just what we expected, a bucket.
Yeah. I can. I thought you guys would appreciate that, especially if you've ever bought something from IKEA. So it's. But I don't know if it was an update to Zoom, but I think it was just a feature I didn't realize was that I can go and pick a custom graphic to use as my background. And so I was just kind of, I wonder what I should put up there. And then I stumbled across this one and I go, oh yeah, you guys will like this one. All right. Well, I'm going to go ahead and stop the recording here, but we're welcome to continue our discussions.